Hello everyone, my name is Chia-Wen. I'm from the Repo Lab at Georgia Tech, led by Dr. Kira. In this video, we're going to present our work in CVPR 2022, Beyond the Pre-trained Object Detector, Cross-Modal Textual and Visual Context for Image Captioning. In this work, we first identified the potential issues of encoding the input image with a frozen pre-trained object detector. For example, the detector may be good at encoding object-centric information, but may fail to encode other information such as object relationships, scene or image level information, and so on. Therefore, we propose to retrieve textual context, as shown on the right figure, to provide complementary information to the detected objects. Furthermore, since the detector is not jointly optimized with the image captioning model, the feature representation of the detected objects may be suboptimal for the target image capturing task. Therefore, we propose to refine the features of the detected objects by conditioning them on the visual context. By incorporating the proposed textual and visual context, our method achieves significant improvements over previous state-of-the-art. Current image captioning methods typically encode the input image with a frozen pre-trained detector. On the right figure, even though the object detector may be good at encoding object-centric information, such as the man and the racket, it may fail to encode other information, such as the object relationship, for example, man holding a racket, or image and scene level information, such as tennis court and outdoor scene. And obviously, since the detector is not jointly optimized with the captioning model, the object features may not be optimal for the target image captioning task. To address the first issue, in the left figure we propose to incorporate textual context retrieved from image subregions by a multimodal clip model to provide complementary information. Specifically, we first construct the caption database by encoding the captions from some caption dataset, such as Microsoft Cocoa or Visual Juno, by using the text branch of the clip model. We then query the caption database with the image subregion encoded by the image branch of the clip model, and then get the top K most relevant text description of the query image. To address the second issue, we propose to refine the object features by conditioning the features on the visual context encoded by the multimodal clip model. As shown in the figure below, the input image is first encoded by the image branch of the clip model. The image feature is then concatenated with the object feature, and then an FC layer is applied to refine the object feature before ascending into the captioning model. Similarly, the textual context is first encoded by the text branch of the clip model, and then refined by the image feature before ascending into the captioning model. The textual context and the detected objects are then concatenated along the sequence dimension into a long sequence. The concatenated sequence is then fed into the captioning model for caption generation. Under the setting without transformer pre-training, by incorporating our proposed visual and textual context, our method achieves significant improvements over previous state-of-the-art by 7.2% in CIDR and 1.3% in Boodle 4. The reader may be curious to ask, why don't we just jointly train the clip model with the image caption model? There is a concurrent work, ClipVile, that jointly trains the image branch of the clip model with the image caption model. As shown in the table, their method requires a much larger ResNet 50 X4 backbone to achieve comparable performance with ours. Training the image captioning model jointly with such a large backbone is computationally expensive. On the other hand, our method only uses a VITB32, which is equivalent to ResNet 50 computationally, and everything is computed offline. We also experiment with a strong Vimbo pre-trained detector, and our methods still achieve a significant performance improvement. This indicates that a strong pre-trained detector still misses some important information, which can be provided by our proposed visual and textual context. When incorporated into an Oscar transformer pre-training method, our method again achieved a substantial performance improvement. This means that our method also works well with the transformer pre-training methods, and that our visual and textual context provide information other than the object tags provided in the Oscar method. Thanks for listening. More analysis can be found in the paper, and we'll also release our code and our proposed visual and textual context.